Chemical Engineering. I'm really excited to be here because I've been getting emails from Mike Brenner for the last 2 weeks saying how great this place is and how fabulous you all are. So this is the schedule for this week. Mike Shelley and Mike Shelley from Toronto are going to be co-running the next 2 weeks, so there's going to be a lot of exchange between those 2 weeks. As you can see, we've had a slight schedule change. Heinrich Jaeger's flight actually doesn't get in until this afternoon, so we've shifted the schedule. We're going to have the talks in the morning, and then your afternoon is free, and then we come back for your research talks in the evening. Okay, so let me just quickly introduce to you your speakers for the week. So like I said, I'm Pekka Hosoi. We have Jean-François Joigny right here, who's going to speak right after me. Jerry Gollick, who I saw, Jerry Gollick right there, and Ayusaman Sen in the back over there. And Heinrich will be in this afternoon, so feel free to sit with them at meals and ask them all kinds of questions and all that kind of good stuff. Okay, let's see. Do we have any other announcements?
No.
T-shirts? Do we have any T-shirt questions? All good?
Not right now.
Okay, good. So I'm just going to jump in. You should interrupt me at any time. I've kind of gone through the notes, so I know roughly what you guys have seen, but if it's stuff that you've seen before or if you need more background, just interrupt me. Okay, so the next 2 weeks are going to be about active matter. And biofluid dynamics. Okay, and I'm sure there are going to be many people who will give their own definition of these two things, but I'm just going to give you a very broad definition of both of them so you know what's coming. By the way, these are very much related topics, I'll say. So it's not that we're going to do 1 week of active matter and 1 week of biofluid dynamics. They're all going to be intermixed. So active matter, roughly speaking, is assemblies of active or say self-propelled particles. Maybe I should put particles in quotes. There's lots of things that might do this. So examples, some of which you will see, some of which you might not, are swarms of bacteria. Schools of fish. So you can see why this is closely related to biofluid dynamics. Let's see. Let's say driven granular systems. Field-activated fluids. So a field-activated fluid is something that has got particles in it that might respond to an electric or a magnetic field. Hopefully Heinrich will say anything about that. Right, and so there's a lot of interesting behavior that can emerge from these kinds of systems. Biofluid dynamics, we're going to take a very broad view. Biofluid dynamics is basically just the intersection of biology and hydrodynamics. Intersection of biology and fluid dynamics. Okay, and this is what I'm going to start today. So I'm going to give a little bit of an intro lecture on biofluid dynamics. So for starters, what I did is I just went online and I just started looking for pictures of biofluid dynamics. So let me turn this off. So here's a bunch of stuff. This is a random collection. There are many other topics that you might come across. Here's a bunch of examples of biofluid dynamic systems. So you might include insect feeding, hemodynamics. So hemodynamics is blood flow, microbial ecology, drinking. Drinking is a big topic right now. High Reynolds number swimming, low Reynolds number swimming, flying. Medical engineering, that's another good one. Let's see, non-Newtonian transport, I'll talk a little bit about that on Thursday. Drag reduction, transpiration, filter feeding, biofilms, developmental biology, ciliary transport, adhesion. So this is just, like I said, I just went online and just started picking out pictures. So there's all kinds of stuff that might fall under the theme of biofluid dynamics. We're not going to be able to touch on all of these, but you will see some of these in the upcoming week. If you want references of these, I don't have references off the top of my head, but I do know who's working on these projects. So if there's something that you're particularly interested in, you should just ask me, I'll give you some names. Okay, so today, though, we're going to concentrate on swimming. So I'm going to do an introduction on swimming. Okay, so swimming. So I guess the first thing we can ask is, what is swimming? So you can think for a minute about how you might define swimming. So roughly one definition of swimming is cyclic deformations. Cyclic deformations. And I'm going to put cyclic in parentheses because the deformations don't necessarily have to be cyclic, but oftentimes they are when you're talking about swimming. So it's cyclic deformations of a body that result in a net translation and or rotation. So that's basically swimming. I'm also going to put in parentheses, just to sort of clarify a little bit, usually with no externally applied forces or works. Right, because if you're just pulling an organism through water, that doesn't really count as swimming. Okay, so this is saying that you're gonna move your body around in some way and go from here to there. Fine. Okay, so if you're going to talk about sort of optimal or good strategies for swimming, obviously this is going to depend highly on the Reynolds number, probably your favorite dimensionless number that you've seen all of you. So strategies depend on the Reynolds number. And if we're going to think about biofluid dynamics, you have to think about what kinds of Reynolds numbers are you going to see in biological systems. Okay, so the first thing we're going to do is estimate typical Reynolds numbers in biological systems. Right, and as you all know, the Reynolds number, so let's just remind ourselves, the Reynolds number is equal to rho u v, or let's call it L, over mu. Right? Or if you wanted to do it in terms of the kinematic viscosity, UL over nu. Good? Okay, so the first thing in estimating typical Reynolds numbers in biological systems is that biological systems tend to move around or tend to involve water. Right? So the interesting thing about the Reynolds number, if you look at this, there are two parameters that are going to change wildly across different species, U and L, the speed and the typical length scale. But these two guys, the material parameters, these are not going to change a whole lot because water is water, right? Blood is basically water, other things. There are exceptions to this, and we'll talk about that on Thursday. But for a large part, if you're thinking about swimming, this is going to be the properties of water. So, so in fact, actually, does anybody know the kinematic viscosity of water? Yeah, good. 10⁻⁶ in what units? In SI units. Yeah, that's good. Okay, good. So that's basically fixed. Okay, so now all you have to do is you have to pick the velocity and the length. Okay, so there's another rule of thumb which is so sketchy I'm not even going to write it on the board because I don't want any record of it, but I'm going to tell you what it is. Okay, and so the rule of thumb is the following.
Videographed.
Oh, okay. Yeah, just turn off the video for the next 5 minutes. I'm just kidding. Okay, so the rule of thumb's fine. So L, you can look at an organism and you know roughly how big it is. Check. Okay, but now you have to decide how fast it is. Okay, so roughly speaking, the speed that organisms move is their length per second. Right? So for example, I'm on the order of a meter, so I move at about a meter per second. Right? A swimming microorganism is about 100 microns, and they move at about 100 microns per second. An ant is a millimeter, it moves at about a millimeter per second. And obviously it's biology, so this is really, really rough. Biological systems do all kinds of crazy things. But if you want to know roughly where your Reynolds number fits, and you want to take a rough cut, it's not a bad estimate. Okay, you may now turn on the video camera again. Okay, so let's make a chart to see where different biological organisms might fit on this scale. Okay, so here you go, here's Reynolds number. Okay, so let's say that right here I've got a Reynolds number of 1. So my up here, this is Reynolds number, this is my length scale. Okay, so a Reynolds number of 1. Okay, so in a Reynolds number of 1, I know this is 10 to the minus 6. If I want to make a Reynolds number of 1, it means my length scale should be about a millimeter. Right, so organisms that are about a millimeter, throw them in a bucket of water, they have a Reynolds number of about 1. Okay, so let's see, Reynolds number 10. 1,000, 10 to the 4, 10 and 6. Okay, and let's go this way as well. I'm going to go all the way down 10 to the minus 5. Okay, so 1 millimeter. So a centimeter is going to be sitting somewhere over here. So these are organisms that are about a centimeter. Here are organisms that are about a meter. Okay, and conversely, this is 100 microns, and this is at 10 microns. And again, this is very, very rough, but it gives you some sort of an idea of where things will sit. Okay, so bugs. So if you're thinking about bugs, bugs are going to sit somewhere in here. A bug. Okay, so these are bugs. Right? And again, it depends on how good they are at swimming, right? So, ants aren't very good swimmers, so they're probably down here somewhere. Okay, people tend to sit somewhere around here. Here's people. Depending on how good of a swimmer you are. Okay, microorganisms. So there's sort of 2 different kinds of microorganisms. If I think about something like unicellular things, so something like Chlamydomonas, which we'll talk about later. Chlamydomonas. These are unicellular organisms. Okay, they tend to sit somewhere around there, and then bacteria are even smaller than this. So bacteria are kind of down here. We'll talk a little bit about the differences in structures between these guys. Okay, so that's sort of how things sit. And as you can well imagine, the strategies that you might use down here are very different than the strategies that you're going to see up here. And in an hour and a half, you can't do the whole thing, so we have to pick one side. So today, in my lecture, I'm going to focus on this part, basically up to about there. Okay, which means that we're going to be thinking about unicellular and bacterial organisms. On this side over here, so Mike Shelley, I think, is going to hopefully going to talk a little bit about this side, and hopefully Jerry might say a few things about this in his talk as well. Okay, so let's see over here. Okay, so today the topic is going to be the physics of low Reynolds number system. Okay, physics of low Reynolds number system. So we'll start, I'll just put up the equations of motion. So I think you've all seen these before. So we're going to start, since it's low Reynolds number, we're going to start with Stokes equations. Yes? Everybody seen those before? Yes. Yes. Okay. So these are the Stokes equations. And Stokes equations are basically tell you something about conservation of momentum. Okay. Then you also need something about conservation of mass, which is this guy. Right, so this is the reversibility. conservation of mass. Okay, if you need a refresher, you can always go back to Mike Brenner's notes from the first day. And then the other sort of interesting constraint on these systems is written right here, where I say, in swimming, we're usually talking about organisms where there is no externally applied forces or torques. So in general, you also apply the condition that the sum of the forces is 0, and the sum of the torques is 0 on the organism. Okay, and that basically says no MA on the organism. Okay, so in a minute we'll do some examples where we solve these things exactly. But first I'm going to talk about some general things that come out of this framework. Okay, so talk about general themes. By the way, did anybody give a lecture on low Reynolds number and flows at all? Yeah? No? Oh, good. Yes? Oh, maybe? Yeah. Some people say yes, some people say no. Good. People skip that lecture.
The title was not low Reynolds number, but.
Oh, but it wasn't. Who was it?
There were some topics.
Yeah.
That David Carey talked
Oh,
about.
David talked about. Okay, so you probably did it in the context with the surface tension? Yeah. Okay, good. Oh, perfect. Good, good. Okay, so, all right, so general themes of low Reynolds number swimming. Okay, the first is reversibility. Okay, so did David show you the G.I. Taylor movie on reversibility?
No.
Oh, good. Okay. So probably most of you have seen. How many have seen the G.I. Taylor movie on reversibility? Okay, so a lot of people have. But some people haven't, and everybody has to see that movie. Okay. So especially if you're going to do a summer school on hydrodynamics, and it's such a great movie, so we're going to watch it anyway. Okay, so most of you know this idea of kinematic reversibility. Actually, let me write something else on the board. So the problem with doing things at low Reynolds number is that the Stokes equations are linear. Okay, and time does not appear explicitly in the equations. Okay, and because of that, these equations exhibit something called kinematic reversibility. So let me just show you the classic movie, which most of you have seen, but it'll get you into the right framework for thinking about low Reynolds number, right frame of mind for thinking about low Reynolds number swimming. Okay. Oh, by the way, this is the other good thing to know. All of these movies from the National Committee for Fluid Mechanics Films are online here. So if you want to see, this has got boundary layer visualizations. This has got low Reynolds number flows. This has got, and the amazing thing about this archive is this was something that was done in the 60s and 70s. So there's none of this computer-aided visualization, PIV stuff. I mean, you really have to do everything, doing these beautiful experimental techniques to so they do things like hot wires to do bubble flows. It's an incredible archive. Okay, so what I'm going to show you now is one movie that's in this archive, which was done by G.I. Taylor. Okay, so here's the movie. So the movie, for those of you who haven't seen it before, he does the following experiment. He has two concentric cylinders, and there's a fluid in here between this one and this one. And he puts a blob of dye right there, and then he's going to rotate the inner cylinder. Okay, so here's the movie. Okay, so there's the and the gap is small. The gap that you can kind of vaguely see is right about here. Okay, so he puts the blob of dye in there. You'll be able to see the gap a little better in the next part of the movie. So this is a viscous fluid. So you can see the gap. Here's the edge of the inner cylinder right here. Okay, so he takes this thing and makes it thin. And I turned off the sound, but if you hear the sound, you can hear Taylor counting. He counts like 4 turns, something like that. Okay, fine, good. Now we've got it mixed. And then he goes back the same number of turns. And it comes back. So, for those of you who have not seen this movie before, I just blew your mind. For those of you who have seen it before, good movie, okay. So this is the issue with kinematic reversibility, and there are implications for this when you're swimming at low Reynolds number, because when you're swimming at low Reynolds number, it means that everything you do is going to be reversed as soon as you deform your body back to where it was. Okay. So of course the seminal paper on this was done by Purcell. So here's Purcell. So if you're looking for the first reference on swimming at low Reynolds number, it's this one right here. So this is Life at Low Reynolds Number by E.M. Purcell. And he points out that because of this kinematic reversibility, if you deform your body in a reciprocal manner, you can never go anywhere. Okay, so he calls this the scallop theorem because scallops look like this. And so he points out that if you're a scallop and you do this, you go somewhere over here, but if you're at low Reynolds number, then when you do this, you go back to exactly where you started. So he says scallop can never go anywhere, and he proposed that, okay, so the simplest organism that can swim at low Reynolds number is this guy over here, which is a three-link swimmer, which has 2 hinges and 3 rigid pieces, so he can do this. Okay. So he said, okay, so I could deform it in this kind of way like this, and Purcell says in his paper, he says, in fact, I worked this one out just for fun, and you can prove from symmetry that it goes along the direction shown in the figure. So directions shown in the figure is going this way. And then he says, as an exercise for the student, what is it that distinguishes that direction? So he says there are some very simple symmetry arguments you can make to determine which direction this thing is going to go. And then, let's see, so when was this? This was 1976. So then I would say for the next 20 years, physicists proceeded to argue about which direction this thing actually goes. Okay, so if you don't see offhand which way it should go, that's okay. So more recently, it hasn't been resolved which way it goes. I think this was maybe 5 years ago. I don't know, maybe now 10 years ago. There was a paper by Becker, Curler, and Stone who figured out which way this thing goes, but they did not do it using symmetry arguments. They actually simulated the whole thing. Right? So I still don't know what the symmetry argument is. So anyway, so that's something, you know, if you can go through the rest of the talk, you can see if you can figure this out. Okay, so that's the first challenge. Okay, so let's see. So Purcell. Let's see. So let me. Okay. So Purcell. Let me put the lights back on. Okay. So Purcell proposed some swimming strategies that are intrinsic to the swimmer in order to generate motion. Okay. So Purcell proposed some strategies that are intrinsic to the swimmer to generate translation. Okay, so here's just some examples. So this was one of them, the three-link swimmer. Here are some other ones that he proposed in the paper. But more recently, there's been a lot of work thinking about extrinsic strategies to actually break this symmetry and allow you to swim at low Reynolds number. So let's see this one here. So one of the first things you might do, okay, so this is going to be strategies that are extrinsic to the swimmer to beat the scallop theorem. Scallop theorem. Okay, so the scallop theorem is the theorem that says you can't go anywhere if you deform yourself in a reciprocal motion. So the first thing you might try is to make things soft, which seems appropriate since this is a summer school and soft condensed matter. So make okay, so one thing you might do is you might put your swimmer near a deformable interface. right? So that might be a free surface, or it might be a membrane, or it might be an elastic solid. So membrane, elastic solid. Okay, so what does that gain you? So if I have a swimmer that's near a deformable interface, let's say this is deformable, my swimmer goes by, it generates some flows. Those flows will deform the interface. That deformation of the interface introduces some nonlinearities into the problem through the geometry. Now that you've got the nonlinearities in the problem, you no longer have this problem with the linearity of reversibility, and so now suddenly you can actually generate some kind of locomotion. So there are lots and lots of interesting problems involving putting swimmers near boundaries. Okay, so that's one thing. Actually, maybe I should, here's a reference. So, trio. So this is a paper that we had in 2008. Theorem. 2008, which does some of the basic scaling arguments for how close do you have to be, how big do your flows have to be in order to actually exploit this to have your swimmer move forward. So the other thing you can do is you can add some soft microstructure to your fluid. Okay, and this is a funny way of saying make your fluid non-Newtonian. Right? So you add something like polymer chains or something that deforms within your fluid. This is another way that you can break the symmetry and allow yourself to swim even if you're at low Reynolds number. And there are many, many, many papers on this. I'm guessing that next week we have a lot of speakers who are going to be talking more about this topic. Okay, so that's sort of reversibility. So you have to do something about reversibility, but there are ways to handle it. So the next thing let me talk about, as far as general themes, let me talk about force balance. Okay, so that was theme number 1 was reversibility, and theme number 2 is force balance. Okay, so force balance is going to be related to the geometry of the swimmer. Okay, so let me just put up something that shows you what the sort of typical geometries for low Reynolds number biological swimmers are. Okay, and this is what the image I'm going to show. This is actually done by a fluid dynamicist. This was done by James Lighthill. And so this is really a fluid dynamicist's view of biology. Okay, so here's a fluid dynamicist view of biology. Oh, that's what it looks like. It's a mess. Okay, so fluid dynamicist view of biology. So the reason this is actually okay, so this is up here. This is the reference over here if you want to find this. This is clearly done in the days before PowerPoint when you had to draw all your slides by hand. Okay? And the nice thing about this is that Lighthill has arranged this not in any sort of biological way, but he's organized this first and foremost by how things swim, which is exactly what you want to think about this from a fluid dynamics point of view. Okay, so how things swim. So the first thing he does is he has this circle in the middle. Okay, the circle in the middle, everything that's inside of this circle basically consists of a head and n tails, where n is a small number. So as a physicist, this is basically, everything in here is basically a sphere with something, with a rod coming out and, well, 1, 2, or 3 rods coming out of it. Okay? So that was his first sort of cut at how you might actually organize biology. Okay. The second thing he did is he said, okay, let's see, so now I'm going to put in a more traditional biological dividing line, which is this line here. Okay, and that line separates the prokaryotic cells from the eukaryotic cells. So prokaryotic cells are in that hemisphere here. These are eukaryotic cells. And if you remember from high school biology, prokaryotic cells are basically bacteria, and eukaryotic cells are everything else. Okay, so everything, this is algae, this is grasshoppers, us, whales, penguins, everything is down here, and bacteria is up there. Okay. So, and it turns out this distinction is important because the mechanisms of how they wiggle the tails is different if you're a prokaryotic or eukaryotic cell. Okay, so let's see.
Is something on the axis, or how is organized?
Oh, yeah, in this direction. How has he done that? Yeah. So the rough division in this direction is that these guys over here are sort of more animal-like, and these guys over here are sort of more plant-like. But the distinction at this scale is very blurry. So it's a, you know, and again, so this is sort of Lighthill's conception of that. Yeah. Good. Good. Okay. So that's sort of what biology looks like. So there's a couple of things to note, and the first is that these guys over here in the circle here, which are really sort of the motile guys, they all have a feature in common, which is that they tend to have these very skinny tails. Okay, so the question is, why would you want to have a very skinny tail if you were an organism swimming at low Reynolds number? Yeah, so let me tell you that. Let me talk about that first, and then I'll come back and tell you about the distinction between those two tails. If I forget, you can just remind me to come back to that. Okay, so why would you want to have a skinny tail if you're swimming at low Reynolds number? Okay, so from a physics point of view, the way you normally do these calculations is you say, all right, I have some force, some propulsive force, and then that is balanced by drag. Okay, so for example, if I take a sphere and I drop it into a fluid, I have gravity that's pulling it this way, and I have to balance that by drag. If I'm a fish, I have a tail that's swimming, it's shedding vortices, so it's got some inertia that's pushing it this way, and that has to be balanced by drag. The problem at low Reynolds number is there's no inertia, there's no gravity, there's nothing to balance drag, right? So the only thing you can use to balance drag at low Reynolds number is drag, which is a weird thing. Okay, so how does that work? Okay, so force balance. So you have to use drag to balance drag. And it basically runs something like this. So here's my little organism, and it has some kind of a skinny tail. Okay, so let's zoom in on this tail. So we zoom in. Okay, so that little thing looks something like this. So here's that segment that I just put this is a piece of the tail right here. Okay, now suppose that organism takes that tail and it moves it up. Okay, so it's moving the tail up at some velocity u. So it's moving at some velocity u. So I can break that velocity, obviously, into components that are both aligned with the tail and perpendicular to the tail. So I've got some velocity. So this is u perpendicular, and I've got some velocity component. U parallel. Okay, so at low Reynolds number, the force, the drag force, this is the drag force, is proportional to the velocity. And I'm going to come back to this and we're going to do a dimensional argument and show why that has to be true. But for now, just believe me that the force has to be proportional to the velocity. And so I can again split this into two components, which tells me that the force, the perpendicular drag force, is going to be equal to some drag coefficient in the perpendicular direction times the perpendicular velocity. Okay? And the force in the parallel direction has to be equal to some drag coefficient. So these are two different drag coefficients here. Times the velocity in the parallel direction. Okay? And it can be shown or it can be measured that again, for a slender object, at low Reynolds number, CV perpendicular is approximately equal to 2 times the parallel drag coefficient. Okay, so what does that mean? So let's just draw this on the picture. So that means that I'm going to get some drag force in the parallel direction, which looks like this. Oh, maybe I should do this in color. I have colored chalk. Okay, so I'm going to have some drag force that goes this way. So this is going to be F drag parallel. Okay, and then I'm going to have some drag force in this direction, which is going to be 2 times this. Okay, so it's going to be, let's see, if I made that about the same, so that's going to be about the same as this. I'm going to run out of space to get the picture. Okay, I'm going to run this through my equations. Okay, so this is now going to be F perpendicular. Okay, and so you can see that the resulting force vector is this guy here. I should have drawn my picture smaller. So this is now going to be my total drag force. Everybody happy with that? Let me say it again. Okay, so I know there's going to be a drag force that is going to be, so if I look at these two equations, I have a perpendicular drag that is proportional to v perpendicular, and a parallel drag that is proportional to v parallel. Okay? So here, this is v drag parallel is proportional to u parallel, and but the way I sketch this, I made this to be about 1, right? Because I made these the same size. Okay, so that's fine. Okay, and so then I say, okay, parallel. In the parallel direction, or in the perpendicular direction, I know this has to be about twice as much as the drag force of the parallel, so I have to take this and I have to do it twice. Because there's 2. Okay? And then I combine these and I get a vector that looks like that. Okay, so the total drag force is going in that direction. Does everybody believe that? This is very key. Okay, so now the interesting thing about this, so notice that even though this thing is moving in this direction, the drag force, most of the drag force is going that way, which is what you'd expect, right? If I go this way, there should be drag pushing me that way. Okay? But because of the geometry of this object, there is a small component that's going this way. Right? And it's that small component that's going this way that gives you the propulsive force. Yes? Okay, good. Okay, so that is how you use drag to balance drag. Right? You have to have some kind of anisotropy in the drag coefficients, and you have to have some kind of clever arrangement of geometry in order to get this thing moved at low Reynolds number. But in fact, that's important enough that I'm going to write it down. So, so we need, so propulsion comes from the anisotropy in drag. Okay, so let's see. All right, so that was the first very simple calculation. Let me go back to this here. So I said you can use a dimensional basically some kind of a scaling argument to figure out that that has to be true at low Reynolds number. So let's talk about dimensional analysis. And drag. This is just kind of a fun calculation. So I know Mike did Buckingham Pi with you guys, right? Mm-hmm. Yes. So everybody knows Buckingham Pi. By the way, did anybody else do dimensional analysis of drag? Okay, good. All right, so let's do the following. So suppose, so let's just think about a sphere. So let's say I have a sphere, and let's say that sphere is moving. Let's say I'm pulling on this to make it move at some velocity v. Okay, so my sphere is moving in that direction at some velocity v. Okay, if the sphere is moving through fluid, so I have some external fluid. That external fluid has some material properties. So it must have some viscosity and some density. Okay? And it has some geometry. So the sphere, let's give it a diameter v. Okay? So if I take that sphere and I move it through this fluid, it's going to experience some drag force going in this direction. Okay, so there's going to be some drag force at v. Okay, and I'm just going to now use dimensional analysis to see if I can figure out what that drag force should be. All right, so Buckingham Pi theorem tells you, all right, I need to count my variables and then I need to count my dimensions. So I've got, okay, the first part of this calculation you've probably seen before, but the second half is where it gets good. Okay, so number of variables. So my number of variables are, it's fd, d, mu, rho, and v. Right, so that means I have 5 variables. Okay, my number of dimensions. So number of dimensions are going to be mass, length, and time. Mass, length, and time. Okay, so I have 3 dimensions. Okay, so Buckingham Pi theorem tells me I should have how many dimensionless numbers? 2. Good, so I should have 2 dimensionless numbers. Okay, so let's just make those dimensionless groups. Okay, so we'll call them pi 1 and pi 2. This is the Buckingham Pi theorem. Okay, so pi 1. So you guys can probably look at this collection of variables and tell me what the first dimensionless group should be. Reynolds number. It's got to be the Reynolds number, right? I mean, it's a fluid mechanics lecture, so it's got to be the Reynolds number. I have variables that I can make a Reynolds number out of that. So pi1 is going to be rho v over mu. Okay, that's my first dimensionless group. Okay, so now let's make a second dimensionless group. So I've used everything except FD. So my second dimensionless group must be some dimensionless version of FD. Okay, so it must be something that's like this. So FD, and if you put everything together the way you make a dimensionless group, one way to do it is to go rho b squared b squared. Okay, you'll notice I left some space in there because historically speaking, and there's no reason why you would do this, but historically speaking, there are some dimensionless constants that go in here. So typically this is written in the following way. It's got a 1/2 here, and it's got a pi over 4 here, which makes this a cross-sectional area. Okay, so if you hadn't put those, if you didn't know to put these numbers in, that's totally fine. You have a perfectly fine pi group without them. But as a nod to history, we put those numbers in. Okay, and if you put those in with a nod to history, this becomes CD, which is the drag coefficient. Okay, and that's all we get, because Buckingham pi tells us you only get two dimensionless groups. Okay, the other thing the Buckingham pi theorem tells you is it says, okay, so I noticed in Mike's notes he wrote it the following way. Right over here. So in Mike's notes he said, Buckingham pi tells you that the physics is all described in some function, which is a function of pi1, pi2, which is equal to 0. Right? That's Buckingham pi. I can always rearrange this. Okay, and I find it more useful to think about this instead of this way. I'm going to solve this for pi1 and say that pi1, actually I'm going to do it in terms of pi2. Pi2 is some function of pi1. Right? Everybody believes that I could take this and solve it for, and write this way. Okay, good. Okay, so what does that do in terms of the numbers that I have? So what that tells you, so we've written our numbers down there. So that tells you that the drag coefficient, CD, can only be a function of the Reynolds number. Okay, for any sphere, for any fluid, for anything that's going through this thing. Okay, so this is how far Buckingham pi takes us. So Buckingham pi says this must be true. It does not give us the functional form. Right? Dimensional analysis will never give you a functional form, but it tells you that if I go and do a bunch of experiments, I'll see something that looks like this. CD versus Reynolds number, and there's going to be some functional form that does something like that. Okay, so now we're going to see if we can cheat a little bit and go a little further and figure out what that functional form is, again without doing any calculation. Okay, so suppose the following. Everybody good so far? Yeah? Okay, good. Okay, so now suppose the following. Suppose I was interested in certain limits of this. So let's consider the following limit. Let's consider Reynolds number much larger than 1. Okay, so if I have a Reynolds number that's much larger than 1, let me write down my list of variables or of parameters that I thought were important. So I've got FD, rho, mu, v, and v. Okay, so Reynolds number much larger than 1 says that I'm in an inertial limit. So in an inertial limit, do I still need all of those variables? What does Reynolds number much larger than 1 tell you? What can be neglected relative to what? Viscosity. It means I can neglect viscosity relative to inertia. So what does that tell you about that list of variables? I don't need viscosity. Okay, so over here in this region of the plot, viscosity can't be important. All right, so now what do I have? Now I'm left with 4 variables. I still have 3 dimensions, okay, which means that I only have 1 dimensionless group. So 1 dimensionless group. Okay, so let's write that down. So we'll call this my new pi1. Okay, so my new pi1. So viscosity is not in there, so I can just make the same as my old pi1. Right, I can still make it the same as that pi group I had before. Okay, so I only have 1 pi group. So what does that tell me in terms of Buckingham pi? So Buckingham pi says that one of my pi groups, it can only be a function of the rest of my pi groups. Okay, so this pi group can only depend on the rest of my pi groups. The rest of my pi groups are nothing. So that means that this has to be constant. So that has to be constant, which tells you that in high Reynolds number, CD, my drag coefficient must be constant. Okay. So I have now done something interesting on this plot. Okay. I now know that this doesn't look like this out here. It looks like this. There's a high Reynolds number. All right, let's do the other one. Okay, so on the other side, so now let's think about low Reynolds number. Okay, so part 2. What if my Reynolds number is much, much less than that? Okay, so now I've got a drag force, I've got V, D, rho, and mu. So at low Reynolds number, is there something there that I can get rid of? So remember, low Reynolds number means that inertia is not important relative to viscosity. So what is the parameter there that characterizes inertia? Maybe. Proposal for V? Maybe. What is inertia associated with? Mass. Mass. Inertia is associated with mass. So what over there is going to characterize the mass of my object? Density. So at low Reynolds number, I can get rid of this. Okay, good. So now let's make another pi group. So again, there must be only one pi group because I've got 4 variables. Okay, so pi 1 is going to be equal to FD over mu d. Okay, and again, since I only have one pi group, this must be constant. Okay, and so if I rearrange this, this tells me that FD must be proportional to mu d. So as promised, I have just shown, oh, I erased it. But over here, I had something that said F is proportional to V. Right? So as promised, I've just shown you that at low Reynolds number, the drag force has to be linearly proportional to V. Okay, now let's do one step further. So now let's rearrange this a little bit. So let's put this in terms of what I have on my plot over there, which is CD and Reynolds number. So I'm going to take this equation. Let's divide both sides by rho d squared d squared, rho d squared d squared. Okay, this side is now what? CD. Okay, and CD must be proportional to, what do we have here? So V's cancel, V's cancel. I'm left with a mu over rho Vd, which is the Reynolds number. So this is great. So this tells you now at the limit of low Reynolds number, the drag coefficient is proportional to 1 over the Reynolds number. So if this is a log-log plot that I have over here, I now know that this side doesn't look like this at all. It looks like this. The slope of -1. Okay, and then something complicated happens in here. Something always complicated happens in transitions. Okay, so does this actually work? So here's the data for the ionosphere. There it is. It's kind of blurry, but you can see. So there's this. So this is CD versus Reynolds number. The Reynolds number goes from 10 to the -1 to 10 to the 5 up here. So you can see up there, you get a slope of -1, and then it goes to a constant. So not too bad, considering that we did absolutely no calculation. Right? I mean, we haven't solved anything with the Stokes equation. We didn't solve anything with the Stokes equation. But you can actually get the behavior in this doing this sort of asymptotic dimensional analysis. Okay, so we'll bask in this for a minute, and now I'll show you the problem. Yeah?
Why does the transition occur at something like 10 to the 2 or 10 to the 3 versus what we would naively would expect 1?
Actually, that's a good question. You know, I don't have a good answer for you on that, but let me think about that. That's a really good question.
What was the question?
Ask me again tomorrow. So why does the transition happen here, which is at like 50, instead of here, which would be 1? Right, so, yeah, that's an interesting thing. Oh, actually, I think I might know the answer, but let me check. I'll answer that question tomorrow. Okay, so, any other questions on this, by the way? Good. Okay, so here's the problem. The problem is I covered up the right-hand side of the plot, and it really looks like that. So, now, okay, so my question to you is, what the heck happened here? Does anybody know what happens here? Yeah.
The boundary layer becomes turbulent.
That's exactly right. That's exactly right. So what happens here is the boundary layer becomes turbulent. And remember, to get this constant, what we said is that we can neglect viscosity. And as soon as the boundary layer becomes turbulent, then you can no longer neglect the viscosity in the calculation. Now, it turns out that if I kept going, you would get rid of that again, and it would flatten out again. Well, but in any case, so it's not perfect. In dimensional analysis, you always have to be a little bit careful with it. But it's not bad. Okay, so that was my aside on drag. Let's see, what do I want to do next? Oh yeah, okay. So now we're going back to my list of themes for low Reynolds number swimming. Okay, so my list of themes for low Reynolds number swimming. So that was so my first theme was reversibility. The second one was force balance. My next one is going to be efficiency. Whenever you're talking about swimming, people usually talk about optimization, and whenever you optimize something, you have to have some kind of a metric to determine what you're optimizing. Okay, so we use a metric to quantify what we are optimizing. Okay, so I'm going to tell you the two metrics that are usually used in low Reynolds number swimming, and I have to say, I personally think that there are better ones to use, but I'm going to tell you what's always used in the literature. Okay, so generally when you're talking about locomotion, you either optimize, so you will either want to maximize speed for a given power consumption. Okay, so this is if you're, say, a sprinter. Okay? Or you want to maximize efficiency for a given speed. Okay, so this is endurance. Okay, so let me just write down the definition of efficiency for low Reynolds number. Okay, so efficiency, when I say efficiency here, okay, people usually call that EF, efficiency. So in general, when you're defining efficiencies, the standard way to define efficiencies is you want to put what you want on top. Divided by what it costs. And ideally this measure is going to be dimensionless. Okay? So for swimming, what do I want? I want to get from here to there. Right? So for swimming, what I want is the useful work. Okay? And so the useful work in getting me from here to there. And if I take some kind of a circuitous path, like if you look at the trajectories of low Reynolds number swimmers, they tend to do something like this. Right, all of this motion is not useful to me, so it's only the work going in that direction that I care about. Okay, so I want the useful work, and at low Reynolds number, pretty much what it costs is your viscous dissipation. You're dissipating all kinds of energy there. So this is going to be rate. Actually, this is going to be. Let's make this the rate of useful work. Easier to do in terms of rate and the rate of viscous dissipation. Okay, so the rate of useful work. So the rate of useful work is going to be force times velocity, right? And then that's going to be divided by, I'm just going to call my dissipation phi. So there's some function that characterizes your dissipation. Okay, I just told you the force is proportional to the velocity if you're at low Reynolds number. So that means that this is going to be some coefficient, which is going to depend on your geometry and your your swimming strategy. Times v squared, right, because this is alpha times v, divided by phi, your rate of dissipation. Okay, And so this guy here, this is sort of the power that your motor has to put out. This is assuming that almost all of your energy goes into viscous dissipation, which is a pretty good approximation at low Reynolds number. So this is the power that your motor that comes about here. And that is that if you look at these two standard measures of how well am I doing, these two standard metrics, they're identical at low Reynolds number. Right? So look at that in the context of that definition of efficiency. Okay, so if I want to maximize speed for a given power consumption, okay, so that tells me that I would want this is fixed, and I want to maximize this, which tells me I want eta to be as large as possible. Okay, so that's this metric. This says maximize efficiency for a given speed. Okay, so that tells me fix this and make this as small as possible. So again, I want my efficiency to be high. So this measure, so at low Reynolds number, these two guys are exactly the same. And the reason for this again is because in the Stokes equations, you can always scale out time. Right? So time has a funny meaning when you're talking about the Stokes equations. Okay, so let's see. So that's the first thing to know. Let's tell you about efficiencies. Let me check my notes and see if there's anything else I need to tell you about efficiencies. Oh yeah. Okay, so Purcell talked about efficiencies. Okay, so let me actually write this down. So typical efficiencies. And I should also say this is the standard definition that's sort of used in most of the literature. So if you go back and you look at Taylor's paper, if you look at Purcell's paper, if you look at
I'm sort of confused by these equations. Is the total force on a swimmer should be zero? Is that sort of an integral hidden here over the?
Oh yeah. Sorry, that's a very good question. Very good question. Yeah. No, I said this badly. Yeah. So this force, again, we're talking about the useful work. Okay. So imagine this is my swimmer. So that force is the force associated with the work to move it from here to here. So that force is the force that you would have to apply if you took this swimmer and you just dragged it in this direction at the swimming velocity. Yeah, that good question. Anything else? Good. Good. Okay. Very good. Okay. So so Purcell. So if you look at typical efficiencies for low Reynolds numbers, using that definition. So typical efficiencies are about 1 to 2%. Which is pretty lousy, right? If you do, so I'm going to do in a minute if I have time the Taylor sheet calculation, which gives you an efficiency of about 7, which is about as high as you can get using this. And it's because everything is so dominated by this viscous dissipation at these scales. Okay, so if you're reading a paper, so this is a little. Okay, so if you're reading a paper and the person is citing efficiencies of 10% or more or something like that, you should look at the definition of efficiency because it's probably not the same definition that was used in Lighton, et cetera, et cetera. Jerry, you have a comment?
What force? You put it in the numerator there.
Yeah, so exactly, yeah. So let me actually draw that a little bit better. So suppose this is my swimmer. Okay, suppose it's going this way. Okay, so the way it's typically defined in these papers is the useful work. Okay, so the useful work is the work that you do to move this object from here to here through the fluid. Okay, so the force that you put in, this is F, is the force you would need to apply to drag the swimmer at the average swimming velocity right? So if you have a sphere, that force is going to be your 6 pi UVV, right? If you have a funny shaped object, it's going to have some other coefficient for it. And again, there are many, many other ways that you could define efficiency, but if you go back to sort of the classic papers, this is what they use. Yeah?
Do you have a reference? What's the efficiency for fish or for men?
Oh yeah, that's a good question. Ask me that in 20 minutes and I'll show you a plot. Other questions? But actually, as far as I have a very interesting efficiency number, which has nothing to do with percentages. But so I went to a robotics conference where they were talking about walking, about the efficiency of walking. And so A, the efficiency of walking, and B, how good we are at storing energy in our bodies. Okay? And it turns out that with the energy stored in the fat in your body, you should be able to walk 3,000 miles without stopping for food. Now, there are other things that will go wrong before that happens. And there are many other things that will break in your body. But if it's just a matter of energetics and you're converting the fat to energy at the, with the efficiencies that you convert in your body, you should be able to walk from LA to New York without eating. Amazing. It's an amazing system. Now, like I said, there are other things that will break down, which are less amazing, but still. This is actually an interesting number because it seems like biological systems are fairly efficient, but if you look at low Reynolds numbers, you're fighting against so much drag that the efficiencies are just not all that great. Let's see. Oh yeah, so I should say, so Purcell, in his paper, he worried about this. He didn't like these numbers because it seems like, biological systems should not be that bad. So in fact, he then did the following calculation. And I don't know why he did the following calculation because I don't know why this tells you more about biological systems. But he said, okay, let's instead of writing down this efficiency, let's calculate the power per mass for the organism. Okay, so Purcell did the following calculation. Okay, so he said, let's instead look at the power per mass. Okay, and for a microorganism, he got something on the order of 0.5 watts per kilogram. Okay, and it turns out that if you compare that with larger organisms, it's about the same. It's kind of ballpark. It's even a little bit. It's it's pretty good actually. So why that would be a better number to look at, I don't know. But this is something that he measured. He calculated in that paper. Okay, good. Let's see, I think that's my end of my overview of themes, and now we're going to do an actual calculation. You guys have questions on this so far? Yeah?
I actually want to go back to this issue of reversibility.
Yeah.
In real life, the scallop theorem doesn't work. And the reason is that you have Brownian rotations.
Oh, yeah, yeah.
And so, if you didn't have Brownian rotation, the scallop goes like this, you go nowhere.
Yeah, right.
And if the Brownian rotation is too high, it just spins in
Yeah,
go nowhere.
yeah.
In between, you actually
Yeah.
go somewhere.
Yeah, I totally agree with you on that. Okay, this is a very interesting point, and I'm going to say it in a slightly different way because I have a student who worked on a similar problem, but it's exactly what you said. So here's the issue. So in a perfect world, the scallop theorem is the scallop theorem, and you do this, and then you do this. Okay. So I had a student who was working on optimizing maneuverability. Right? Because obviously efficiency and speed are not the only things you can optimize. If you look at the fish that swim in coral reefs, they're funny shapes, right? Because they're optimizing for something else. Okay, so we started looking at, can you say something about optimizing for maneuverability? And she did the following calculation. She said, okay, well, so if you're talking about maneuverability, I have to reorient myself. I have to say something about reorientation. So she said, let's look at the simplest problem you can think of, which is the scallop. Okay, so here's the scallop. Okay. And then she said, but let's suppose on this scallop that the center of buoyancy is slightly off from the center of mass. Okay, so let's say that this is the center of mass. Actually, let's make this the center. Let's make that center of mass. And let's make this the center of buoyancy. Okay, and so that tells you, so if this thing was not doing this at all, what it's going to do is it's just going to tip up like this. Right? That's the standard, that's the lowest energy state that it wants to be. Okay, but now imagine you're trying to swim when you do this. Right? So when you swim, you open this up, you tip a little bit this way, and then you close and you tip a little bit in another direction. Right? So now you have a method of breaking the symmetry because you have this extra sort of degree of rotation where you reorient yourself as you swim. So if the time scale, so like what Usman said, if the time scale for this is very, very slow, then you're back to the scallop theorem. Right? Because then you just do this and the time scale for reorientation doesn't do anything. Okay? If the time scale for this is very fast, you're also back to to the scallop theorem because it just tips up like this and then you do this. Right? But if the timescales for reorientation and flapping are somewhat of the same timescale, then you have this interaction between this dynamics and this dynamics, which you can actually break the symmetry because you're in a different position when you open up as when you close, which is what you need to have. Right? And so Biofluid has pointed out that in fact at low Reynolds number, if you're looking at very tiny organisms, you get this sort of this kind of reorientation just from the Brownian dynamics, because the things can reorient. So as long as your timescales are matched, such that this timescale is comparable to this timescale, then you can break the symmetry and you can actually swim. Yeah, that's a very good point.
You're talking about just Brownian motion.
Just Brownian motion. Just Brownian motion, yeah. Yeah?
But on average, in a situation like you said, you go nowhere, right?
Well, I mean, you probably do something else, right?
So you have an enhanced diffusion, but on average, you still go nowhere.
No, you do.
No, because I mean, you could just as easily flip it the other way, right?
Okay, and if you want to show the plots, I'll show it to you later on this week. But yeah, you don't actually do because you're not going back to where you started. And so what you've done is you've moved and then you've gone like this.
Yeah, over a long time.
So yes.
Over a long time on average.
What does it mean square displacement, but no mean displacement? Mean square displacement,
Yeah.
right?
Yeah.
Okay.
So if you had no rotation, you would be just going like this, right? And if you had too much rotation, you're just going to go like this. But in between, over a certain time interval, you will sort of go a finite distance, which you wouldn't have if you didn't take into
Sure, on
account
small
rotation.
time scales, but on large time scales.
Oh yeah, yeah. On the large time scale, everything looks wrong.
Right, that's probably, yeah. Good. Are you going to show plots of that in your talk? Oh, good.
No, I wanted to ask you.
Oh, yeah.
I wanted to make a point about the move, about the G.I. Taylor moving.
Yeah.
Everybody looks at the reversibility, but if you look carefully at the edge of the blob,
Yep.
you actually see that it is diffused. It has diffused significantly,
Yep.
which is true only because of the rotation. Because if you would not
Oh,
see
the timescale's
diffusion,
wrong
you would
for-
not see
I see.
diffusion
Yeah.
normally.
Yeah.
But because you have enhanced the velocity gradients,
Oh, yeah.
the concentration gradients by the rotation, so that everything is long and skinny,
Right, right. Oh, that's interesting.
then
Because you
you
can
actually
diffuse
do
across
get
streamlines
you
then.
get
So you-
diffusion,
yeah.
and it's actually visible there. So it isn't
Yeah.
really quite reversible.
Right, right. So in fact, actually, if I turn on the audio, Taylor says that at the end of the video. He says, notice, you know, we've almost gone back to where we started, but the blob is now fuzzy, right? And the fuzziness comes about from diffusion. And actually, I didn't know that, Jared. So Jared's point is that if you just look at the normal timescale for diffusion, it's too short for it to diffuse. But because you have this shear going on, you can now diffuse across the streamlines, which enhances the diffusion. So you can actually visualize fuzzy. That's an interesting calculation. So here, homework. Everybody figure out how far that blob should have diffused. Given you know how fast it moved, you know how big that gap is. We'll ask you for the answer tomorrow.
Of course, that doesn't bear on the scallop theory.
Right, exactly. Yeah. Good. Other questions? Okay, good. So let's go. Let's just do a quick calculation since there's not a lot that you can do analytically, but there is a very nice one, which of course was done by Taylor. So it's good that we come back to Taylor. Okay, so here's one of the simplest swimmers you can imagine, which is Taylor's 2D waving sheet. Okay, so this is one of the earliest calculations for low Reynolds number swimming. I'm not going to go in detail through all the algebra, but I'm going to outline the steps so you could fill it in if you wanted to. So Taylor did the following calculation. He said, all right, suppose I have a sheet, and it's an infinite sheet. Okay, so it goes off in this direction, and it's 2D, so it goes kind of like. Right, so it's I didn't draw that well, but it's a 2D sheet that's doing this. Okay, and he said, all right, let's parameterize this the following way. So he said, let's say this is, let me get this right. So he said, I'm going to call this y naught. So this is y direction, this is the x direction. So why not, he said, is equal to, so he put in some waving form here. K of x minus sigma t. Okay, and he said the following things about the sheet. He said it's inextensible. What else do I have to tell you? Infinite. And small amplitude deformations. Okay? Oh, and so there's going to be some velocity field outside, away from the sheet, u, which I'm going to characterize by u. Okay? Okay, so let's see. How do I want to do this? Let's do like this. Okay, so Taylor said, all right, let's solve this in the following way. So the Stokes equations can be rewritten in the following way. As a biharmonic equation where this is the stream function. Have you guys seen the stream function yet? Good. Okay, so the stream function, so this is your typical stream function. So u is equal to minus psi dy, and u is equal to psi dx. So have you done the exercise where you take Stokes' equation and you rewrite it as this? Yeah. Yep, okay, good. Good. So Taylor just said, okay, let's just solve that equation. And he said, okay, he said, suppose small amplitude. So he said bk is much, much less than 1. So I can expand into small parameter. Okay, and I can do separation of variables. And if I do separation of variables, I can just write down sort of the general solution to this. Okay, I'm going to write down the general solution to this. You can convince yourself that that's really what it is. Yeah, you plug in it to show that that's really what it is. Okay, so the general solution to that is 1 over sigma psi is equal to the sum over n odd infinity of a n y plus bn. So these n's are subscripts on these coefficients. E to the minus ny. So it looks like a normal series solution, right? And z, I should tell you, z is equal to, so define z as kx minus sigma t. K plus, some of it and even. You can see I haven't memorized this because I really didn't memorize this. C1 plus bn e minus ny. Cosine and z minus y over sigma. Okay, so now in order to find these coefficients, of course, you have to apply the boundary conditions. Okay, so the boundary conditions that you apply are no slip at the sheet. Right, so the velocity over here is given by the velocity of the sheet. You're sitting on the sheet over here. And the velocity at infinity has to go to 0. Infinity in the y direction. Okay? And infinity goes to 0. Or, better yet, go into a frame moving with the sheet, and so then the velocity at infinity goes to minus v. So that's an even easier way to do it. So, or okay, so now the next thing you have to do is you have to figure out what are we actually solving for. So now this has just become a big algebra problem, right? So I have these boundary conditions that I have to satisfy. I know the shape of the sheet. I know what happens in infinity. I know I have to figure out all my A's and B's and C's in here. But the interesting thing that you're actually solving for is, of course, V, right? Because this is unknown. Right, so that's one of the unknown parameters in this equation. And so what you really want to know is how fast does this thing swim, right? If you get the A's and B's and C's, then you get the velocity field, which is great, but you know, I mean, this is what you really want to know. Okay, so Taylor does that. So he does the algebra, and after about a half a page of algebra in his paper, so after about 1/2 a page of algebra, Taylor finds V is equal to 0 at lowest order. Okay, so that's like, this is now, I'm up to the first 2 pages of the paper. Okay, so of course, after you find that the velocity goes to 0 lowest order, so this means that this thing doesn't swim, which is completely useless, right? I mean, you can't publish a paper if you say that thing doesn't swim. Okay, so the next thing he has to do is he has to say, okay, well, so to lowest order this thing doesn't swim, but now I have to go to next order in BK. Okay, so now, like I said, now I'm up to page 2 in the paper. Now we skip ahead to about page 12 or so, after many pages of algebra later. Okay, so this is the bulk of the paper. He finds, and again, it's just, again, solving for those coefficients and solving for V to this order. What he finds is that V over C, so C, remember, was the wave speed of the sheet that was imposed, okay, is equal to 2 pi squared B squared over lambda squared times 1. Okay, so that's the next order, right? So that's in order B squared over lambda squared, so that's good. It swims in second order. He also went to the next order, which is why it took him 12 pages of algebra to get there. So the coefficient is 19 over 4 times pi squared B squared over lambda squared. Okay, so the sheep does swim, albeit very slowly, but it swims. Okay, and so the interesting thing is that if you now compare, so Taylor got interested in this because he'd seen movies of swimming sperm, so that's why he wanted to do this calculation. So if we want to compare this to actual biological data, so he decided to ask, okay, how far does the sheep go after one cycle? Okay, so how far does the sheep travel? In one cycle. Okay, and you find that it's approximately lambda, which is the wavelength of your sheep, divided by 84. Okay, so it doesn't move very, you know, I mean, here's your wavelength, and you do one, here's your wavelength, and you do one cycle, and there's hundreds of that, right? So the thing is not moving. It's, again, it doesn't move very efficiently, but it does move. And if you compare this number to what you see in swimming microorganisms, it's actually not that far off. It's pretty, order of magnitude, it's pretty good. So Taylor was pretty excited about that, and that I think is sort of one of the first swimming calculations that was done. Okay, so what do I have to tell you next? Let's see. So I only have 10 minutes left. Yeah, okay, I'm just going to end up by showing you a couple of movies
Can I ask a question?
Yeah.
How much is this number of the
Oh, how does this come about from this? Yeah. So, let's see, so I have to remember how you do this. Yeah, so you have a velocity. So you can integrate your velocity. A cycle is lambda over c, yeah. So in fact, I should say...
Why does B disappear? That's my question.
Oh, say again?
Why does B disappear?
Oh, why does B disappear? That is a really good question. It's been a long time since I did this calculation. I have to check. This may come from this part. I mean, I think certainly if you put it in, then the amplitude is gonna matter. So let me check that tonight. I suspect it's that you integrated that part, and then the B cancels out. Yeah.
So, solving this problem, considering only the linear terms, gives kind of the wrong ones, right?
Correct.
Because then higher terms
Yeah.
give what we actually see.
Yeah.
So what actually those higher terms capture, I mean, what physics do those higher terms capture which are not captured in the linear?
Oh, which are not captured in the linear terms. Yeah, so, yeah, that's also a good question. So,
Linear term is necessarily zero digit symmetry.
Yeah.
So the first non-zero term has to be plotted out. Or
that doesn't really answer the question about,
You get the linear
well, I
term.
guess it sort of answers the question about physics.
yeah,
In the
it's not
sense,
symmetry.
I guess you're asking what is the physical effect that comes in at the next order?
Well, yeah.
Right, right. So what changes about the flow field that allows you to break the symmetry?
Or it's like, what do we actually neglect with higher terms, which
Yeah.
actually gives us this result?
Yeah. Well, yeah. I mean, so
The linear term is reversible.
I mean, you can always say what what you always say about the linear terms that at Stokes law everything is symmetric, so you won't get anything. But I'm not sure if that's so I don't know. So if somebody knows the answer to this, you should speak up. I think that we would actually have to look at the flow field to see what's breaking symmetries. I don't see it offhand by looking at the equation, but I haven't looked at the flow field. But I don't know. Do you guys know what happens at the next order in this calculation? Okay, we have a room full of experts on low Reynolds number, and we don't know what happens in the flow field the next order. Oh, good. Homework problem. Plot the flow field the next order and see what comes in. Yeah, that's an interesting question. It's good. I'm trying to think. I'm trying to think. I'm thinking back to the paper. I'm not sure if Taylor actually commented on that, but I'll put I think the reference is in the notes that I handed out, so you can take a look at the Taylor paper. But most of it really is going through the algebra to get to that result from there. Okay, good. I'm gonna pull up another movie. So stretch and talk amongst yourselves for 30 minutes while I pull up this next movie. I'm just gonna end with a movie to give you a teaser for what we're gonna do next. Okay, so since we only have about 5 more minutes, I'm just going to show you some movies, and then we'll talk more about this next time. So the next step you can do, there's not a whole lot of calculations you can do analytically. Eventually you have to do something numerically. So I'm just going to show you some results that were done by my student Daniel Tam to look at optimal swimming strokes. So he did the following. So he said, okay, suppose I have an organism that has basically got a spherical head and a tail, or 2 tails. The movie I'll show you is got a single tail. Okay? And he said, okay, I can represent that organism by a series of Stokes lists. Do you know Stokes lists? Oh, okay. Okay, so Stokes lists are singular solutions to Stokes equations, and you can put combinations of these to basically satisfy different kinds of boundary conditions, right? So you put a series of Stokes lists together to represent the tail. You put a series of Stokes lists together to represent the head, and you choose them in such a way such that you have something that's roughly close to a no-slip boundary condition satisfied here, and this is you have some kind of slender body that does something like this. Okay, and it's sort of a fast way to do the computations. So here I think he's got some references there for the slender body theory, for the exact singularity distribution, and for the lowest order interactions. And so he did this code, and then he said, all right, let's do a calculation to figure out what shape of the tail as a function of time optimizes the swimming behavior of this guy. Okay? Okay, so you do that. So there it is. That's the optimal. Okay, it's exactly sort of what you expect. That's what swimming microorganisms look like, right? That's what swimming microorganisms look like. And you always get something where you have a traveling wave that goes from the head to the tail. You always, and actually I should tell you, this is not a sinusoidal wave. What you generally see in these calculations is you see regions of localized high curvature that are connected by straight segments. Okay, so that's actually what you're seeing here. So regions of localized high curvature, which propagate down that way. And these are sort of, both qualitatively and quantitatively, this is sort of what we see in experiments. So the calculation, since I think I'm just about out of time, the calculation that I'll talk a little bit about next time is, so beyond kinematics, can we say something about morphology of swimming microorganisms? So can we say, for example, if I've got this head, how long of a tail should I put on this if I want to make this thing an optimal swimmer? Okay, so I'll let you think about that until we talk next time. And so now I think we've got about a 30-minute break, and then Jean-Francois will do you have any questions actually before we break? Yeah.
Do you always impose that it pushes the organism, or do you allow it to push the organism?
Oh yeah, so we don't.
Because both exist.
Yeah, exactly. So we don't impose either of those. So what we say.
Always more efficient to push.
With one tail, it's always more efficient to push. With two, not at all clear. With two, you can go both ways.
Yeah, because what biologists say is that in the animal world,
Yeah.
it's pushing, in the plant world, it's pushing, it's pulling.
With one tail or with multiple tails? So I think, so I'll tell, actually there's, I would say with one tail, the optimal stroke it's extremely robust. Like you could put in guesses that are not even close to this. You could put in things that are pushing, that are pulling, that have funny shapes, that are anything. It always converges to this with one tail. Always converges to this. With two tails, it already becomes more complicated, and you can see both movers and pulls.
How do you keep the boundary condition between the flagella and the organism?
Yeah, exactly. So exactly, yeah. So the boundary. So remember, so these are all eukaryotic cells. Okay, so which means that the organism is allowed to apply a torque anywhere along the tail. So there's no motor here. The boundary condition that we do so obviously, anytime you get things that are close to each other, the numerics is not good, right? But we do put in a first order correction, which is the Faxén's law to do to the lowest order correction between the flagella and the head. Having said that, I still wouldn't trust that, right? Because we don't do it exactly. We do it as distance. Good. Other questions? Yeah.
I have a question about efficiency.
Yeah.
The 10%, however you want to define it. Is there, well, one thing is why is it so bad? And can you imagine other swimmers that, is that a physical limitation?
Yeah, so, okay, so the reason it's so bad is that when you're moving at low Reynolds number, you just have to fight to get through this fluency, because every time you move anything, you're fighting viscous dissipation, right? So it's you sort of expect it to be very bad. I have seen papers in which people have calculated an upper bound on efficiencies, which tend to be, I don't know, 10%, 17%, something like that. But again, it depends on their definition of efficiency, right? So the one that we used, again, is the one that people sort of used originally. Maybe that's the right one to use, maybe not. But pretty much you're always going to be bad at low Reynolds number just because you're in this very viscous environment. So every time you do anything, you dissipate a tremendous amount of energy. Yeah?
This efficiency, am I right that this efficiency still doesn't include the thermal losses where you have a metabolism that goes directly to the heat without any mechanical energy in between? So it's actually even worse.
It's even worse. Exactly. It's even worse. Yeah. And so the argument there is that because you dissipate so much in viscosity, is that you say, okay, that's the bulk of the energy that I'm losing. But really, if you think about the way the organism generates these things, it has to eat, and then it has to convert that into mechanical energy. So you're saying that those internal mechanisms of converting that energy are efficient enough that they're a small correction onto what you're losing in the viscous environment, which may or may not be true. Like you said, it's probably worse than what we have. Oh, I promised to show you fish efficiencies. Okay, I'll tell you what. Let me just check and see if I have them. Okay, let me just show. This will be really quick. No, it'll take me a while. I'll show you the first thing after the break. Okay, so when you come back, the first thing you'll see is fish efficiency.